So mostly we're going to be talking about recommendation systems today. We talked about clustering last time. I'm going to sort of continue and give a quick introduction to how we might map some of these clustering techniques onto MapReduce. But it's not going to be very deep. I'll come to that later because I want to get into recommendation systems. And the way we are going to do it is that today I'm going to give you a general high-level overview of recommendation systems. In the next lecture, I'm going to go significantly deeper than we have in the previous lectures into the mathematics of it. So I'm going to try to motivate it today so that we are left with 2 mathematical concepts for next time. And I want you all to do some background study because I'm going to go fast. This is not within the scope of this class, but I still want to cover it. But it's probably much better if you come at least read the Wikipedia entries for these things before you come for class next time. And following that, we look at sort of the parallelization aspects related to clustering recommendation systems, and specifically these 2 techniques that we're going to look at next class, which is SVD, which is singular value decomposition, and sum optimization techniques. Okay, so today's class is going to be relatively low-key, so you can go back and you can finish up your assignments. But please read up on these topics, and I'll refer you to specific cases at the end of this thing. Please submit your reports. Assignment 2 is going to be using, for MapReduce, we are going to be using the apt cluster, which is from the Flux group at the university here. All of you should, as soon as possible, email the TA your SSH public key. And please choose it such that you have it named as the username that you want, .key or any other extension, but let's just stick to .key. Does everybody know how to generate? Has everybody used SSH keys for authentication? Do you know how to generate it if you don't have one? So just do a man SSH keygen. You should do this from the machine that you're going to be using. So if that's the laptop you're using, generate it there and send it if it doesn't already exist.
Can I send more than one key?
Preferably not. Why do you want to send more than one key?
I want to have my desktop in office.
Just share the same key.
Okay.
You can use SSH config and specify the same key or you can do that.
For users, one key. Okay.
Just do it just so that it's simpler. I don't want
Okay.
them to set it up. This is for authentication. The way you're going to access the cluster and you're going to run these things, I will put it up with the assignment by this evening. So you will find it, you'll find details with some standard examples on how to run it. And the assignment we've talked about is going to be matrix multiplication as well as page rank. Okay? That's what it is going to be. The specific details will be online.
Having more questions is kind of like we had 2 weeks,
Yes.
but we had 3 questions.
Yes.
One is not coding.
You had 3 weeks actually. Yes. Okay. What do you want more time? You want less time? What is it that
I
you
want
want?
to reduce the number of questions so that we take one complex problem and try to solve it rather than having.
This is going to be much easier actually.
Easier.
So I have reduced the workload for this assignment. It's actually very easy for you to do it. Those of you who are used to Java might probably be able to do it in a day if you want.
Okay.
And you should again keep in mind for the next assignment, you are going to be doing some combination of clustering and basically setting up a recommendation system. Okay. Any other questions on this? Mail this as fast because this is going to limit your access, and I would rather, because this is somebody else's resource that we are going to be using, I don't want to nag them repeatedly. So try to get your SSH keys to the TA as soon as possible. Okay? So we talked about clustering, and we specifically talked about k-means. And let me just, even though I don't have a slide up, let's sort of go over it. There were 2 important aspects when we were considering clustering. The first part was that in most of these cases, you want an initial guess. You want a good initial guess. And we discussed some structures for it. And in some ways, you can think of that figuring out that initial guess is also a k-means algorithm. So we're typically looking at two versions of clustering. One version which is sampling the data and relying on a small subset, or is somewhat generating a good approximate guess. And the other one which relies on a point assignment technique to and iteratively update the centroids that you have for your K clusters and gets onto it. So even though I'm sort of saying that we're looking at a point assignment, the same approach or the same ideas, and we'll go into this a little bit more in detail later on, but this is just to give you a quick idea, is that you can say that if the user provides K and you start off with a random map, then, each map, the one way to look at parallelizing this is that each map task has a subset of the points, and it's going to independently generate K clusters, or maybe greater than K clusters, right? So we take data at each map task, generate a bunch of clusters, and output with the same key. So all map tasks are going to produce only one key with a description for the cluster. And this could be depending on what the data was and what algorithm we use. It could be the centroid or some sort of a cluster representation using representatives or anything else. The problem, of course, is that you're going to be limited with a single reducer at the end. You can stack these together somewhat in an MPI reduced fashion, but at the end of the day, you're going to end up with a single reducer which needs to take all of these clusters and merge them. Okay? And if you remember with the different representations we have, we still sort of will end up with a bit of a bottleneck out here. The other problem that you're going to face, and you will, it's why k-means in general, or most clustering algorithms are somewhat not well suited for map reducers, that they end up being iterative. Even if you think of the way in which we were picking out the k initial guesses by starting off with a random point, picking a point which was furthest from it, and so on, adding one point at a time, you're still doing it in an iterative fashion. I'm adding 1 point or adding an extra cluster in one go. So the iterative nature, and in the point assignment technique, we are going through all our data, we are updating iteratively our estimate for where the cluster centers are and where the k-means are centered. So basically the iterative fashion makes it a little bit not very well suited for MapReduce, because there is a lot of overhead after each set of MapReduce. You need to read it, write it to disk, and then read it back for the next iteration. Okay? So when we implement this, we're going to do this in Spark, which will allow you to sort of retain some of this information across iterations. And so it should be much easier, but I want you to think about how easy or difficult it is going to be for you to do this, and both from the ease of programming, which it's not going to affect you much, but from the performance perspective, where the fact that you have to do these additional synchronizations to and from disk really hurt you quite a bit. So I sort of roughly talked about this, but let's just formally go through it. So the way you would do it iteratively using MapReduce is to randomly initialize K centers. This could be replaced, which is basically going to be the same way if you had a smarter way of picking the initial centers. Each point gets assigned to the nearest center. So every single map task is going to get these values for your K centers. And it's going to take each of its data and it's going to assign to the appropriate cluster. We're going to then recompute the centroids based on which points got assigned to which clusters, and then decide to update them and repeat until convergence. From a MapReduce perspective, why is this not working? Okay, so that's going to be your map task, where we take each cluster center. We're going to be producing an update, which is going to be the cluster number or some key, which is going to be an identifier for the cluster, and the updated centroid, which is going to be the guess or the center for the next round of iteration. Okay? So that's going to be your map and your reduce task, and we're going to repeat this until we converge. Is this clear? Okay, I'm going to move on to, yes?
Can I use some standard methods for finding K and then assign clusters?
You can do this. So this gets into the specifics. So if you want, when we look at this specifically, I'll go into some very specific examples. We'll pick a example, maybe corresponding to the recommendation system, and look at how you would actually go about doing these. So again, because I'm focusing only on the computational aspect, I don't want to go into very detailed aspects of exactly how you pick K, how you pick the K centers, and there are a wide variety of approaches for doing this.
The selection of K is not appropriate in the performance might.
It's going to change drastically,
Yes.
and finding the right K is a very hard problem. So in most cases, if you don't have too much of an option, you probably are better off sampling your data, using a more complicated approach on a single node, not in a distributed fashion, estimating what appears to be a good choice for K and go with it. Or as you will see when we do the recommendation systems, and where we will use clustering as a sort of a component within this, you can do this in a hierarchical fashion, even though you're doing it distributed. So you say that I expect K, let's say, to be around 10, but I'm actually going to not do it that way, and I'm going to start off with a much larger set of K, cluster it, and then try to cluster the clusters again themselves, and do it in almost in a hierarchical fashion where you build up a tree, which allows you more flexibility. It's a chicken and egg problem, right? You're trying to cluster while you are trying to estimate right? So you want to solve both those problems together, which is that you're doing some work clustering it and at the same time trying to estimate. And you can then define metrics which allow you to choose the appropriate number of clusters then. So you build a full hierarchy there. And we'll sort of do it a simplified version here today. Okay.
Just add something. So if you think about it, it's completely unsupervised. You're given data, and you are supposed to cluster it, and you don't even know if the data itself is clusterable.
Yeah.
So it's
Yes.
especially if you have high dimension, where lots of data, it has like, I don't know, thousands or hundreds of dimensions. How can you even know that your data is clusterable? So we somehow hope, right, that there are some groups in these high dimensional spaces.
Can't we use a variance function and build the endpoint, see whether
So you can do all of that, but like I said, typically that's you bringing in your intelligence somehow, and that's why I'm saying that you can group that as some sort of an analysis that you have done a priori or from prior knowledge, just from the fact that you know the nature of the data, that you can think about it. But having an open-ended, if I don't know anything about it and you randomly give me some data, it's a very, very hard problem, because I don't know anything about it. In most of those cases, it's either going to be where you understand the problem itself at a sort of a more human sense. Like I said, we're grouping animals, so I know how many animals to expect, let's say, in a farm, right? So I have a rough idea of what to expect. Or you're going to take some sort of sampling, you're going to do some analysis trying to build up that information. And it rarely makes sense to group both of these steps together anyway, because you're just making your life miserable if you're trying to solve such a difficult problem at a very large scale anyway. So you will break it up at some level into these two. So let's sort of look at recommendation systems. We sort of loosely touched on this when we did PageRank and we did personalized search, but let's look at it a little bit more formally, what it means. So fundamentally, at a very, very basic level, you want to predict user responses to option. So I want to have an idea, I have a large variety of things to offer to you as a user. How can I predict which ones you're likely to like more than everything else? So that's the offer. Because I'm limited by how much I can show you at a time, I would rather show you things that you're more likely to like. This is from the search perspective, but it also maps to other cases. You can think in terms of so many news articles, so many news sites. I want to make sure that if I'm offering a dynamic news site to you, I want to offer articles that you're likely to be interested in and likely to read. There's a huge potential from an advertisement perspective, or in general from the commercial aspects of it, which is basically what is it that you're trying to give suggestions that the user is likely to buy or to consume. And this maps across news sites, movies, Netflix is a good example, music. iTunes wants to suggest new artists or new bands that you are likely to be interested in. What books are you more likely to be interested in based on what you've read, or products in general. So, Amazon is a good example, Netflix is a good example. So for a lot of the things that we're talking about today, think of these two. Most of you probably have used it. And that's a good example for all of these cases. So when you log on to Amazon, it's telling you that, this is something that you might be interested in based on whatever logic they have. That's a recommendation system. Or if Netflix is trying to tell you that this is a movie that you should watch, why is it saying this and how do they actually come up with those numbers? And those are recommendation systems. It's important to realize how this relates to the traditional picture, right? When we have looked at, for those of you who were there and experienced the pre-online shopping or online consumption era, and you walk into a physical store, you walk into Walmart, say. The way Walmart suggests things to you is a little bit different because that's not really tailored at you. They're limited by the amount of shelf space they have, the amount of products they can have in the store, have it close enough, and by the fact of how much they want to tailor. They might tailor it to a particular demographic. So maybe there's a huge Hispanic population and they want to have a section dedicated to it, but in general it's not targeted at a specific user. You might have a boutique store which caters to a small subsection of society, but within any of those groups it's not tailored to every individual. And that's mainly because the best they can do and the best strategy that they can have is to use aggregate numbers. This product sells a lot, so I'm going to keep it in my store. This one hasn't been selling. Let me have a sale, flush it out of the system, and then not stock it anymore. So if you think in terms of the products, and we're going to be calling them loosely items to refer to news, movies, any product that you might be interested in, you're going to have some items which are very, very popular. And since it's this late, this is the kind of distribution that you have in your alt debug data set, because that's very common for a lot of real life world problems. So you're going to have very large numbers of a very small set of items and smaller numbers for a very large number of items. Physical stores typically have operated here. And some stores might basically say that we're going to keep a lot of these very popular items, and there might be some random sampling from everywhere else, but that's why if you're looking for something less common, you're more likely to find it at Amazon or some website rather than in a physical store. Yes?
Is Scout suggesting that if the popularity is high, then the number of items is less?
It's not the number of items. It's the so this is not the total number of items. In general, what I'm trying to say is that there are maybe 100 or 200 items which are very popular. There is high demand for a small number of items. This is not a demand supply curve. I'm just saying that there are few items. So think of it like some enumeration of products. This is, I don't know, milk, right? It's very popular. But I don't know, some weird book that only a small set of people are interested in is not very popular. So we're saying that there is a small number of items, there's a small class of items. You can take your most popular physical store, the kind of items that they would carry. They would have maybe a few hundred varieties of items, right? Whereas the total number of items that you would find in an online store is going to be much more. You'll find every single brand, every single variation, and all that. So that's what these numbers mean here. Okay? Is this clear? Now, this is the advantage and the disadvantage from the online firm, which is that if you're looking for something very specific, you can go log on to Amazon or any other store which is tailored for your kind of things. Maybe you're interested in an LP from 1950s. You can go on there. I won't find it in a regular music store, but I can go into a particular case and online store and I can search for it, find it, and buy it. The problem happens so this is usually called as the long tail. So online stores typically specialize in this long tail. So if this is sort of the kind of area where you are interested in, then it's going to be much easier for you to buy it from the online stores. The thing is that most online systems also want to operate here because this is where you're going to make money, right? You're not going to make too much money only by selling items here because they're not as popular. And since their catalogs or the amount of products that they offer is so much larger than a physical store, they need to show it to you. You're not going to be walking around a store, so you're going to be landing onto a web page. So they want to show you from this wide variety of products that they have what they think you're most likely to buy, because that's how you tend to. This is like the equivalent of a physical store having a special booth as you walk in, which is selling maybe Halloween stuff right now because they know that that's in high demand and you're likely to buy it. So this is the equivalent of the online version. Of course, they're carrying way more items and they can do smarter things. And most importantly, they can tailor it for every individual user. So when you log on, you're shown a different set of products, and when you log on, they're shown a completely different set of products. And again, to connect back to the search case, this is what Google does when you're searching, and your results for the same keywords might be different from his. It's in some sense it's a related problem, but there are some slightly different issues which we'll talk about later. Okay, is this clear? The formal definition of the problem. In general, as we did for the PageRank case, it's going to boil down to some basic linear algebra operations. And we're going to define a matrix which we're going to call the utility matrix. This matrix is going to capture the relationship between the users, whom we are going to represent on the rows, and the items, the products that are being offered, whether these are movies or physical products for sale. And those we're going to have within the columns. The matrix entries themselves, so that's the matrix, where the number of rows is the number of users, and the number of columns is the number of items that we have. So you can imagine this is a massive matrix, right? Especially if you consider something like Amazon. The matrix entries are scores or ratings by the user for the products that they might have consumed, bought, or are interested in somehow. Maybe you have a wish list. You go in and say that this is something I really like, or I bought it and I gave a rating. You watched a movie on Netflix and you gave it 4 out of 5. Of course, the scoring that you might have might be Boolean if it's only an option of whether you watched the movie, you didn't rate it, but you watched it, or I haven't watched it, I have no information. It's rarely in the form of that I like this and I don't like it. It might just be that maybe I like it or I like it and I don't know. So that's an issue that we have to deal with. Quite often it might be that you have an ordered set. An ordered set means a set of ratings that you might have going from 1 star to 5 star or any other combination, some small integer values that we can assign to. In some cases, it might be a real number. You can think in terms of given confidence measure or something that we measured over in an average sense. This is going to be harder and harder because in general, as you can imagine, from your own experiences on many of these websites, this information is not very easy to get. You do not go and rate every single object. Some of you might, and some people are very aggressive about giving reviews and rating everything, but most people aren't. So in many cases, we might not have this directly. The most important thing to notice is that it's very, very sparse. And this is somewhat uncertain as well. So if you think about it, it's possible that you like a particular movie, but me as the system designer or the system itself might not know that you like the movie. So in some sense, in the PageRank case, when we were building our transition matrix, we had exact information. It was very precise. A link exists or it doesn't exist. In this case, things are a bit fuzzy. We might have some information, and for everything else, it's an unknown. We don't know if the person likes it, doesn't like it, or to which extent. So what exactly is the goal of the recommendation system, given a matrix of this form, where most of the entries are going to be blank? We might treat it as 0, but in reality they are blank. We don't know anything about it. We want to predict what the blank entries are. So we have some values given, and so we have a sparse matrix given, and we want to sort of generate or an estimate for the dense version of this matrix. Keep in mind that that's a very hard problem, but for most realistic cases, we don't need to predict every entry. It's not the goal. I don't need to know if you're going to like or how likely you are to like every single product out there or every single movie out there. What I would want is to predict with a reasonable high probability a small set of items that you are likely to rate high. To some extent, you can also think that I don't even need to figure out all the entries that you're going to give a high rating to. I just need a subset. And we can repeat this again and again. So I can show you some subsets which I think you're likely to watch the movie or to buy the product, and then you can repeat and generate a much wider sample again. Okay? So at the base level, that's what it is. You have a very sparse matrix and there are entries which are missing and I want to predict them. I sort of already mentioned this, but I'll repeat it again. The question is, of course, how do we get the utility matrix itself, the values? You can ask users to rate items. Not everybody wants to rate. And it's going to be biased, both within and across users. Within user in a sense that maybe Netflix asks you today and you don't have anything better to do and you're going to spend 15 minutes rating a bunch of movies. So you rated some of those movies that you like, but you haven't rated every single thing. So it's only within the user there is a bias that depending on when you were asked to provide this information, you might or might not do it, which means that the information I have regarding a particular user is biased. More importantly, it's biased across users. So some of you might be very diligent in making sure you rate every single movie that you watch or every single product that you buy from Amazon. You go back and leave a feedback there. But there are some who would never do it. I never do it. So that is the other problem. So deciding on a system which relies on user information is difficult. At the same time, if you're a small company with a dedicated clientele targeting a specific market segment, then it might be a better solution because your data is going to be, your size of your matrix is going to be much smaller. But for somebody who's like Google or Amazon, it doesn't make sense, and most of them are going to rely on the second option, which is to make an inference from the user's behavior. The problem here is that making an inference on the quality of the experience is very difficult, so it invariably ends up being a Boolean choice. Maybe you liked it, you didn't like it, or you're interested in buying this product or you're not. You watched this movie or you didn't watch it. It might not be good enough. It's difficult to infer that, no, this person really liked this movie versus he didn't like this movie. So it gives us a wider set of data. So if you're Google or even if you're Amazon, if you can come up with a strategy that if you looked at a product page and you spent, let's say, 5-10 minutes reading that page, right, which can be inferred, maybe at least in a statistical sense, you can have a fairly good idea of that you were interested in this product. Even if you don't buy it, then I can populate the entry in the utility matrix saying that this person is interested in this product or this class of products. Whereas if you rely on only ratings, you're going to end up with a much, much sparser matrix, right? So as mentioned earlier, the bigger the companies, especially people like Amazon who are very diversified, or Google, would have this advantage because they can infer from other sources as well. So your book choices, the kind of books that you buy, might be reflective of the kind of movies that you're likely to like. So there is additional information that can be obtained from here, right? So that's where it becomes a little bit tricky, and this is going to be very, very specific to the kind of algorithms that you're going to use. So your input data is going to determine what kind of recommendation system do you need to design. Also, the quality of the utility matrix, basically issues of how sparse is it, how dense is it, do we have Boolean values or do we have some small integers values reflecting the rating, do we have floating point values giving a much more continuous scale. It's going to decide what kind of a recommendation algorithm we're going to use, and we're going to look at it just now. So fundamentally, there are two major classes of approaches. And it should be fairly clear to you as I describe them where they make sense. The first is content-based systems, which is that they try to take their products or their items and they characterize them with a bunch of properties, right? And so you can think from a Netflix example, this could be the genre of the movie, the director, the actors who are in this movie, and using these properties, think of it in like tags or a feature which describes this movie in some sense. I can decide what this particular properties for this particular movie are. At the same time, I can decide a similar property vector for every user. So he likes this particular movie. He seems to like movies with this particular from this particular director. He likes movies which are sci-fi or whatever, murder mysteries, something. And then we can decide how close is a given movie or a given item to what you like, and that can help us do it. So what it means is that it's a little bit simpler because you are somehow defining what they look like, or you're generating this higher quality meta information which you're then using to figure out or characterize whether a particular user is likely to like a movie or like the particular item. The key thing to notice here is that we are sort of using the same descriptor to figure out what the item is as well as what the user likes, right? So we can now define on top of this, we look at it, a similarity between two items, also a similarity between the user's taste and a particular item. The other, which is sort of, especially for very large systems and large complex environments, a much better approach is to use collaborative filtering, which tries to figure out relationship between users and items. We'll look a little bit at detail in this, but in some sense, what you're trying to reason for the collaborative filtering example is that rather than me saying that here are items that match what the user, a particular user likes, I'm going to say that let me try to find other users who seem to have a similar taste as me, as in they have the same preferences as me. And then based on this, I can be recommended things that he is interested in because he's a similar user or has a similar profile as me. But there are downsides to this as well, which we'll get to in a few minutes. And again, the key issue is that you're recommending items preferred by similar users. There is a different notion out here of how do you define. So I mentioned that you're treating the items and the users the same way in the first approach, the content-based systems. In collaborative filtering, you're trying to sort of say that two users are similar if they've bought the same kind of items, and two items are similar if they have been bought by the same kind of users. So statistically speaking, that's what you're saying. You're saying that there is a direct relationship that if we both are similar, we're buying the same kind of products, and if two products are similar, the same kind of people are buying them. Does it make sense? And that's intuitively the idea behind these two approaches. Okay? So let's look at the first one, which is your content-based recommendations. So we need to first identify these sort of user item profiles and match them for recommendation. Yes?
Okay. So you spoke about the information that we were collecting in the past slide.
Yes.
So what is a good strategy to model all that information?
This is going to be, I'm going to talk about this now, but in a simple word, there is no simple strategy. So in most cases, you're kind of lucky because this kind of information is easy to obtain. In many cases, there is a human agent behind somewhere who has sort of done this. You can think of it like users going and tagging information, right? So let's look at a few cases, right? So if you think in terms of, let's say that you want to create a recommendation system for something like Netflix. Maybe you have your own streaming service, right? And you want to do this. Movies are easy because they're tagged. You can go to IMDb. Somebody has done it, right? The official websites for the movie or these kind of central databases like IMDb will have this information available, including things like genres, actors, the director, the year it was released, where it was shot, what kind of locations, things like that. Whenever you have this kind of information available, it's going to direct you closer to opting for a content-based system, because it is going to be better. Although I talked about the earlier case, and maybe this is a good time to bring this issue up, that in principle, although collaborative filtering sounds better, there is a downside to it, because think in terms of it, right? Consider me and you, right? Maybe there are a set of movies, maybe let's say science fiction. Both of us like science fiction. And so there is going to be, so whatever similarity measure I declare is going to get biased that, yeah, they are similar. But it's also possible that, I like 1920s movies, whereas you don't. And you might like, horror movies, which I don't. So most users are not very one-dimensional. Items can tend to be one-dimensional in a sense that it's easier for you to say that if I liked one particular object, let's say if I am buying a lot of pens, then maybe it makes sense for Amazon to suggest that I look at some other nice looking pens that they have. Whereas matching users will help in a sense, but might not be as foolproof, especially as the number of samples increases. Our choices are not that limited. So wherever you have the option of some kind of structured data, somewhat potentially manually selected, you might actually end up opting for these kind of approaches. In many cases, it might be a combination, which is that wherever possible you use this, wherever I don't have any information, then I opt for the collaborative filtering kind of approaches. There is a positive side as well. Maybe I've never heard this particular band or a musical genre that I potentially might like. And if we both share, we both like rock music, then maybe you have never heard rock and roll and, or old blues stuff. And, because we both share one particular taste, it's possible that you might be. So you could be exposed to other products that you might not have gone looking for on your own. But understand both aspects of it, that fact that it is something which can be a positive as well as a negative. Okay? So in most cases, when you're going for a content-based representation, you're going to have it available. And this is across a number of cases wherein, if you think in terms of book, I know the title of the book, I know the author, I know the general classification for that particular book. The same is true for audio. In many cases, it's going to be a little bit harder when you look at things like maybe YouTube videos, which might not be as formally tagged. If you think in terms of news articles and blogs, news articles from formal sources might be tagged better, but in general they might not be tagged very well. Blogs are probably going to be tagged pretty badly, which means that we have to go in and look at the content, trying to figure out what might be good ways to represent this. So you want to figure out the correct way to represent it. And like I said, in some cases, like the movies, it might be easier. Just developing a system based on using just this kind of like genre, director, actor type information might even work better than you saying that I'm going to go inside and I'm going to have a complicated video processing algorithm which looks at the scenes and tries to extract some information. So this is going to be so problem specific that we are going to skip it, okay, beyond this. Think in terms of what we want to do. So consider the sort of a Google scenario again, where you're searching and Google wants to display a bunch of ads for you, right? So the way we would do it is that the item profile is going to be some categories or keywords for the ads. Again, keep in mind that in this particular case, the vendor who is paying for the ads is probably giving you this as well, right? So it's an easy problem because I already have the categories, I already have the keywords, You're searching for pizza, please bring my location up, and this is the keyword, so you can specify that. I chose this particular example because try not to be limited by, when we talk about a user, don't limit to a physical user as well. For a search case, the user profile is going to be the keyword that the user provided for that particular search, right? It's not you as such. It's not like if you search for pizza once, I'm always showing you pizza advertisements. In this particular case, we're talking of a single search entry there. We're looking at those keywords. We're comparing it against keywords from the ads, and I'm showing those ranked however, correct? It's also important in this case that if you have a problem of this sort and you want to develop a recommendation system, you're always going to go for a content-based approach, because collaborative filtering doesn't really work in this case, right? I have almost an infinite dimensional number of users, right? So you need to factor these kind of issues in when you're deciding on what kind of a system to build. This is probably a good time. Let me just take a small deviation from here, because you all should also start thinking about your projects. This is a good problem, for example, if you're thinking about it, to pick a particular area and then decide it, maybe for movies, maybe for news sites, maybe for tweets, I don't know, whatever, right? So you can start thinking about this and come and discuss with me on what you think. We are still somewhat far from the actual start of the end of the assignments and start of your project, but you should start thinking about it, okay? So make sure that you whatever it is. One other thing, I wish there were more students present out here. I want you all, I'll set up a doodle poll of sorts. If we have to do some extra classes, I want to know which dates and times work well for you guys. There is a lot of material that I would like to cover, and there might not be enough time, so I want to make sure that we are missing some classes for fall break next time. Does Friday work for most people? In general, I would like to at least have a tentative date and time fixed for the odd extra class that we might have to squeeze in.
If it's not this Friday.
Yeah, so I'll set up a poll, and please try to be somewhat flexible in what you enter. That is, don't try to reject it as much as saying that this is something that you will be able to make. There are a lot of students out here, so I'd like to fit that in. Okay. Okay. So let's sort of just briefly look at a specific example. I'm not going too much into depth, and for those of you who pick out projects, we can discuss this a little bit more. If you think in terms of documents, so this could be blog articles or news articles, stuff, information where you might not have precise profiles or tagged information to use as your description, which means that we have to sort of go in and process it. There are 100 ways of doing it. I'm just going for the most common approach here, just to give you an idea of what all you need to think about. The general intuitive notion about this is that if a word occurs very frequently in the text, then that's hopefully a good representative for that particular document. At the same time, there are some words which come very frequently, and those you want to drop anyway, because that's going to be have a very high frequency in every single document. So something that gets used quite frequently to capture this kind of information is TD-IDF, which is basically the product of the term frequency and the inverse document frequency. The term frequency captures how frequently in a particular term is a particular term in a document. So you look at it's a normalized value which captures how many times one particular word occurs in that particular document versus the word that occurs most frequently in the document. So the word, not counting these kind of stop words, that occurs most frequently will be given a value of 1, and one way of saying that that's one of the most important words which characterizes this particular document. And then you're going to have a set of values. So we can define a threshold there. Of course, there are going to be words which are not stop words, which are going to occur fairly frequently in language as well. So we want also a measure of how precise or how subject specific is a particular word likely to be. With the notion being that if it occurs only on a very small set of documents and not uniformly across all documents, then that's a specific word. That's what the second one actually captures, which is that how frequent is a particular term across all documents, right? So if we are talking about I don't know, collaborative filtering, let's think of it a phrase, then we know that we are talking very specifically with regards to this, as opposed to, something like chair or a table, which might occur more uniformly across words. So using these two gives you a reasonable idea of how important and how specific is this particular word to a particular document. And by computing these, we can define a threshold saying that I'm going to use the words with the highest TDIF in the document. Maybe you say that I'm going to choose a 10 top words, or I'm going to choose words up to a threshold of 0.8 or something. And that's what we're going to do to factor in. And this is going to define a vector for us, right? Now the vector, what is the vector going to be in this case? What is the feature vector? What are we defining this on now? In this case, it was easy for the structured cases we looked at earlier, where we said it's the genre, the movie, the director, or the actor. Use the same analogy and extend it out here. You're going to have a long vector. This is the same idea we use for the page rank, which is that for every value that we had, every web page, we have an entry. In this case, we're going to say that here are the most important words, and I'm going to have a variable defined for it. Now keep in mind that we have to do this across all documents, across all blogs, which means that even though I might be picking 10 words from every 10 words to represent each document, in reality, if I consider the entire corpus, then I might have a few hundred words or a few thousand words, right? Because depending on what topic that particular article or that particular web page is about, only some of those values are going to be true. And you're going to get a long vector to the size of the entire corpus, all the keywords in the entire corpus, with ones and zeros, mostly being zero. Again, the same structure, it's going to be mostly sparse, and you're going to be ending up with ones if those words exist. Is it clear? It's the same for the other case. If you think of genres, you might have, say, 20, 30 different genres that you have defined or you have agreed upon, and the movie might belong to one, maybe two, but typically, they rarely go across it. But the director, again, you're going to have a long vector with one entry corresponding to every single director that you have thought of, and a value of one wherever. So these are very, very sparse. And if you remember the discussion we had regarding high dimensional spaces, these are very high dimensional spaces which are very, very sparse, which means that most of these entries are actually orthogonal to each other. Okay? This leads us to the other part. Fine, we have defined these kind of characteristic, feature vectors, so to say, which represent each of these items or the users, right? Keep in mind, this also is the same vector that we use for the user. Which articles does he like? Which topics? He likes articles which have these keywords as the topics. So it's the same issue. We want to define similarity between them, whether it's two items, two users, or an item and a user, right? Those are the combinations that we have to think about. There are hundreds of ways in which you can compare this. I'm just mentioning two very simple ways of measuring. The second one is particularly ubiquitous across. The first is that you should know about at least is the Jacquard distance, which is a very simple thing, especially when you're comparing sets like this, which is effectively saying that I want two items are similar depending on the size of the intersection by the union. So document A has these 10 words which describe it. Document B has 10 words that describe it. I'm going to look at what is the overlap between these two, right? So the overlap, the commonality is going to be given by the intersection, and the denominator here is given by the union size. So you can imagine how you have two sets, and basically the overlap tells you, which is the factor between the intersection and the union, gives you a good metric for how good or how bad it is. Okay. The other option is to use cosine distances, which is basically just the normalized inner product. So you're trying to measure the angle between these values, right? And we'll go a little bit further and we'll revisit them. This is just going to be somewhat like your L2 distance. The other issue is also, how do you figure out what the user likes? I mentioned that, these are the keywords where you use that. And this is actually a very, very hard problem and a very expensive proposition as well, because people are willing to pay money to get this information, which is you can base it off things like search keywords. So Google has a history of, Google early on was anonymous, you just had the page, but then slowly it transitioned into a situation where you are logged on to all the Google websites. So Google has, in most cases, unless you opt out for it, an idea of what you are doing. You might also remember that a few years ago, it was very popular for all of these search engines to give you toolbars. Right? You would install a search toolbar type thing. But fundamentally what they were doing is that beyond search, they were effectively tracking which websites you visit, what do you do. And that's how they were collecting this information, trying to build a sense of what kind of things you like and what you're interested in to what extent. So fundamentally that's what they've been doing over a period of time. And maybe at the end of this class you'll be quite suspicious of every single thing that you see online, because this is what they're doing all the time. They're trying to get an estimate. They're going to try to build a model of what things you're interested in across the board. Anytime you fill out a random survey to get a free sample or free whatever, this is again what they're doing for. They're giving out free stuff and free things because they are interested in getting that particular information. Of course, they can do it indirectly. If you have a blog or if you're tweeting, from your browsing histories, you might have noticed people, they can scan your cookies and get an idea of where all you've been and what you've been visiting. So there are ways in which you can indirectly get this information from the social networks and everywhere else. But I would say the majority is still done through direct approaches where they are actively seeking out this information. How do you actually make recommendations once you have all of this information, which means that I have the user profile and I have an item profile? Then it's easy because I would just use the similarity between the users and the item profiles, any metric, Jacquard, cosine, whatever. In general, of course, to make this fast enough, because you log on, I get your user profile, I need to recommend something to you. You want to, in some sense, bucket the items that you have in some way. And we sort of discussed some of these while we were looking at clustering. You're going to use some sort of a tree structure with some hyperplane representation, which is partitioning all the items. So when you come across, and we can do this because, especially in most of these cases, these content-based systems, we already have our keywords. We know these are things which clearly define which genre you like, so we can clearly define the correct buckets in which to look for. So you're going to use either some tree structure, some sort of a hashing function, which uses this information, picks out the correct subset. You're rarely going to search all the way to the bottom of the tree. You're going to get into a small enough bucket, and then use maybe some other strategy to display the most common, the most likely products that you're interested in. I briefly mentioned here, some of you are probably taking the machine learning class, that you can do this in a more complicated fashion. This is just the simplest way of doing it. But in general, you can build a classifier, you can train a classifier for every single user. Think again, I have a feature vector, I have what we talked of as profiles are feature vectors, and I have a label. He likes it, he doesn't like it, right? He's going to watch it, he's not going to watch it. So it's a simple two-class classification problem, so I can go ahead and train a classifier for this particular problem, and you can have it. It's obviously more expensive because training such a classifier for a very large set of users is expensive. But again, depending on the specific scenario that you are in and what kind of a recommendation system you're interested in, it might be worthwhile to do it. So you need to consider what you want to do and what kind of things you're recommending to what set of users, and maybe it's worthwhile for you to opt for more complicated methods out here. And basically what you're trying to do is to, using the existing ratings, you're trying to learn what the user likes and use that to then predict what kind of a rating he's likely to do for the other options. Okay, so now let's sort of switch gears and look at collaborative filtering. Just to remind you that instead of using an item profile vector, what we do is that we use the column of the utility matrix as the feature vector or the profile vector here. So we're not explicitly determining what kind of keywords or tags define a particular item or a user's taste. In terms of the item profile vector, we're just going to use the column, which is basically the item is defined by which users have bought or rated that particular value. So these are all the non-zeros, right? So if you remember the utility matrix, we had all our users, we had all our items, right? The items made up the columns, and the rows were made up of the users. So if I pick one particular item, which is one column, it's going to be the ratings that all the users gave for that. Or they watched it, they didn't watch it. And that is a sort of a signature for how similar that item is. Make sense? Similarly, if we now consider a row, it gives me a profile for what a particular user's interests are. The user bought some series, rock series. He bought some science fiction books. That defines a kind of a user, right? So we are using those instead of explicitly going through and deciding on what it is. So it's purely based on the information that we have. We're not extracting anything additionally and doing it. We will sort of do something similar, but in a more structured fashion now. Again, it's the same logic. The users are similar if the vectors are closed using some metric, which is basically using either a Jacquard or a cosine function, right? So again, depending on the sets, if two users bought the same kind of, or have a very high overlap in the kind of products that they bought, they are probably similar. Or if the same kind of users were buying this particular product, then those are probably similar as well. The recommendations are based on finding similar users and recommending items liked by similar users. So the way you would generally do it is that I have to fill out the blank entries, correct? That's the goal of this. The utility matrix is sparse with missing entries, and I want to estimate those. So I go to a particular user, say you, and then I look at the feature vector for this, which is basically the kind of products that you've bought. Then through the matrix, I can try to find other users who have bought similar items, and then effectively transfer their ratings onto yours. Okay? So let's say one approach could be that I find the 10 users who are closest to me, right? And probabilistically, I know that it's not that they would have bought exactly the same item. They would have bought another set of items which is not exactly overlapped with what I bought. Average these guys, take their average score, assign it to the value that I haven't looked at, and that's a good estimate. So we need to think in terms of measuring similarity, and because we are using the rows and the columns as the sort of the profile vector, it presents some challenges because it's very, very sparse. I told you that we are almost guaranteed that they're going to be somewhat orthogonal to each other, so we need to sort of use some tricks to, or at least be aware of the issues that are out there. One option is that if we do decide to go for Jacquard, and this is going to depend very heavily on the kind of recommendation system that you're building. Even though we might have ratings, we might want to round it off into just 1 or 0, where 0 would be that is the same as unwatched or not interested because, or missing information. Because this is going to be treated as a negative, which means that we are treating anything that we haven't explicitly rated as unwatched, right? This is good if you're using something like a Jacquard distance where we are only measuring set intersections, and there's only you're either part of some set or you're not. You're not like, I'm 50% part of the set, right? So if you're using these kind of set membership functions and set distance functions, then you want to round it off. A more common thing which you probably should do and work in a wide variety of cases is to normalize the ratings. Why do we need to normalize ratings? He might be a very strict reviewer in some sense, and he might typically give ratings only from 2 to 3. He's not very easily impressed. You might be very easily impressed and consistently will give ratings of 4 to 5. and I'm using this to compare across users. So you want to normalize across the users. It's also possible there are a lot of Apple fanboys, so maybe they give, irrespective of the product, Apple products always are going to get very high ratings. I need to adjust for that as well. So you want to normalize by subtracting the average user or the average item rating from every rating. What it does is that it's going to convert low ratings into negative numbers. Okay? So the average rating for an item or an average rating now for a user is going to be 0 because you've subtracted that. If you think in terms of the physical implications of a cosine distance, it's now going to give you an angle, right? It's giving an angle, which means that if your angle is closer to 0 degrees, then you are very similar. If you're closer to 90, right, which means the value was 0, then you are sort of ambiguous about whether this user really likes it or not. Whereas if you get a negative value there, then basically it's 180 degrees out of phase, then you have a very strong indicator of that this user does not like a particular product or is not really likely to like this particular product. So again, there are other strategies that you can consider, but I'm just giving you 2 examples. If you're considering something like a Jacquard distance, then you probably want to round it off, whereas if you go for a cosine distance, you want to normalize these ratings.
I have a question.
Yes?
So would normalizing still work in the case of when someone, like, for example, I only rate things 4 and 5 because I only rate things that I like.
Yes.
So would that still, would normalizing still make that okay? Like,
It would be fine. So the spread of ratings that you have is there, but it's not affecting everybody else. So when we actually we'll look at a specific example where we are normalizing, where we need to normalize. When we do this formally, we need to normalize across users and the particular item that we are interested in. And then what you have to do is that eventually you will normalize, compute, or estimate the values of all the blank entries. And then eventually when you have to use it, you have to sort of correct that for the normalization that was performed. So what I would do is that in your case, you go from 4.5 to something from say minus 0.5 to plus 0.5, right? That's how I normalize, assuming that your average was 4.5. I'm going to use that, and then using other users, I'm going to predict the values for what I estimate are ratings for everything else. And then I'm going to add 4.5 to that because that's going to give me an idea of what kind of rating that you would have eventually done if you were to have rated it in the first place.
okay.
Yeah. So there are a few extra steps involved, but fundamentally, yes, it's going to map onto it. It's just that when we are comparing across these different cases, and it's not foolproof, it's still a first order approximation that we're doing to normalize them all, because we're not normalizing across all users and across all items simultaneously. We are only normalizing independently and assuming that they are independent of each other, which they may or may not be. Right?
Yeah.
So one important thing is that given the matrix, right, this sort of goes back to what we somewhat talked about earlier, is that there is a duality. You have 2 approaches again from a collaborating filtering perspective, that we can find similar users and average the ratings for the particular item. So we have some missing entry out here, right? I can find similar users, average their values, and that gives me the value for this particular missing entry. I can also find similar items, right? And average the user's rating for those items. In this case, I won't need to worry about normalization, right? So I'm interested in figuring out what your rating for this particular product would be. Based on your purchase history, I try to figure out which items that you have bought are most similar to these. And I average those values to figure out how interested you're likely to be for this particular product. There's no normalization required here. When you consider the other case, if I'm averaging across users, then I have to do that, right?
Yes.
So there are also some other considerations, somewhat computational in nature. If you use the first approach, right, where I find similar users, so instead of finding similar items, I'm finding similar users. So all I have to do is try to find 10 users similar to you. And that's a one-time job for the most part, or at least your tastes are not going to evolve fast enough that I need to do this very frequently. Maybe if I do it once a month or once a year, that's good enough. And for every other product now, I only need to average within this subset. So you've taken something which is a very big problem and I've reduced it specific to every user. If I go for the similar items, then I have to repeat it for every single product, for every single user. So I'm interested in estimating some blank entries in your utility matrix corresponding to you. For every item, I need to find k similar items so that I can average them. And that is computationally very, very expensive. Although, as we talked about earlier, grouping together items is probably preferable. Is it clear? So, maybe better, but this is more scalable. One approach that we would use, and this is sort of where we come back to clustering, is that this matrix is so sparse that the task of finding similar users or similar items is very, very difficult. It's so sparse. And to improve the reliability, what we would do is that we want to cluster these. We can cluster users and we will cluster items. And so effectively, think of it that we start off with a very, very large utility matrix, and we are trying to sort of produce coarser representations of this. Coarser in the sense that there are fewer items. So we're changing from a matrix where there's every single brand of toothpaste and every single tube size, to maybe reducing where all the different tube sizes get clustered into one at some level, and then every brand gets clustered into one together. And so you're basically doing this for users as well. Again, we are relying on the similarity metric that we defined to cluster it. So this goes back to when we were clustering based on the distance metric, right? So the new utility matrix has entries with an average rating that the user gave to items in the cluster. And if you're clustering on the side of the item, then you're basically clustering averaging those values, okay? In general, you want to do this in a recursive fashion. And going back to the question that you asked in the beginning of the class, we don't know k here, right? So what you're going to try to do is to build this hierarchically, and saying that we started off with n items and m users. I'm going to first cluster the items. So going from n, maybe I choose n by 2 clusters or n by 4 clusters, something which is very, very conservative in terms of how much I'm grouping together, right? We're not being very aggressive out here. Once we have clustered the items by taking the averages, we will cluster the users. So reduce m from n to m by 2 or m by 4. And then you're going to recurse, taking this as the input and then clustering the groups further. And so think of like a large sheet of paper that you're folding this way once, the other way once, and so on. So we are compacting it one at a time. We have still assumed that there is an independence. There is a better way to do this, which will come in a minute, which is to actually try to solve this whole problem simultaneously.
What are you doing after you're conservatively clustering items and users? Is there a step to relate them?
Yeah, so at any given time, so we'll tell you how you would sort of use this to fill in, right? So is it clear what you do? All you're doing is that you're reducing the number of items by replacing values by their averages, and then you're reducing the number of groups. So missing entries will get populated by average values wherever you have them, right? Now, you can go back. This is the reverse problem, right? So loosely, if you remember of the way we were doing the scan, the parallel scan, this is kind of what you're doing. You're going from a large problem, you're summing it up to the top, averaging in this case, and now you want to push it back down the tree, right? So you're going back from this compressed notation and passing it on to all the entries which existed. And keep in mind our original definition. We wanted the missing entries to be averages, and that's what exists in this case. So it's very simple. say that we want to find the entry for a user U and item I. We find which clusters they belong to. There's going to be a cluster in the user sense and there's going to be a cluster in the item sense. You find that entry. If an entry exists, which means that it's actually dense at that point, there is a value and it's not blank, then you can simply use that value, right? So in this case, it's just an injection from the coarse matrix directly onto your fine matrix that you have, the full utility matrix. If it doesn't exist, then we can have a fallback strategy like what we discussed, which is to find similar items or similar users and generate an average at that point. The other way to look at it is that at some point we could have continued this clustering all the way till we actually found something which existed, right? In which case the matrix was completely dense. And similarly, if you really want to do it, and that's why I think that the SCAN analogy is correct, is that ideally you don't want to go too high up. So think of a very large matrix which can keep clustering all the while to the point where we have a single group and a single item, which is basically the average rating that all users gave across all items, right? So you don't want to cluster it to that extent. So what you really want to do is to start from the full matrix, and you want to go up this sort of a pyramid that you have to the point where you can find a non-blank entry, and then use that value, because that's
Start from there.
Sorry?
Start from there when searching, right?
No, so how we do this is a little bit messy, but I'm saying from an ideal perspective. That's why, in a more realistic sense, you want to choose a certain level of coarsening or clustering that you will define, go up to that level, and then just use the same strategy otherwise. Okay? Is this clear? How we would cluster each of them and eventually how we end up using? Okay. I'm going to just quickly mention this because I want you to study for this next time. The more formal way of doing this is to really say that the mathematical way of looking at it is that the matrix M, the utility matrix, it's sparse, but it's also most importantly, it's low rank, which means that we can do something like a singular value decomposition, which I will cover next time. In a simplified sense, this is not the singular value decomposition. This is just saying that this is what would be called as a UE decomposition. That we want to approximate M, the matrix, which is n by M, by n by D times D by M matrix, where D is sufficiently small. Okay? The more formal way of doing this is that there is a sigma inverse out here, which is the eigenvalues for the system out here. The eigenvalues. And in this particular case, you would have the full spectrum out here, and the spectrum tells you exactly what the rank is of the matrix. And we can choose a different, smaller subset if needed, as long as the information. This UV, in the most generic sense, is going to only approximate M, especially when D is smaller and smaller. And we need to define some metric on how close this approximation, this decomposition that we have of the matrix is to the original matrix. Okay? And in at least in the first example that we look at, not the singular value decomposition, we're going to look at root mean square error, which is basically taking the square root of the sum of differences over all non-blank entries of M. So we're going to look at singular value decomposition, both how you would do it in a sequential sense very briefly, but please read up about that before next class. More importantly, I want you to, we're going to be covering stochastic gradient descent. At least be aware of gradient descent. So it's a very simple thing. Most of you probably might have done that in any of your numerical analysis class. So this is related to optimizing a function, your steepest descent, gradient descent, these kind of approaches. Make sure you know at least what the gradient descent in an SVD or the singular value decomposition is. And we'll go into both of these aspects and modifications required, because these are tricky algorithms to do when the size of the problem is very large and we have to deal with parallelism. So I'm going to look at variants of both of these, which are the stochastic gradient descent and randomized SVD. Okay? So please read up. I'll put links to both of these on the web page today. So make sure you read up a little bit about this before next class.